I'll start that. What is it? 12:35. Okay. And then I'll get this going again. Okay, I think I got that. All right, now pick this mess up. All right, so now I should be able to share. All right, so let me, when that's gone, scroll down to number 5. This looks like a Gauss's law one here, huh? It says number 5. Hint, a Gaussian surface. A slab of insulating material of non-uniform charge density. Okay. Where X is measured from the center of the slab is shown. C is a constant. The slab is infinite in the Y and Z direction. Derive an expression for the electric field in the exterior regions of the slab. All right, so let me kind of draw the slab, give it this thickness here. And I guess it's kind of three-dimensional, so it kind of goes back. But the real key, and kind of what the picture is trying to show here, is to draw a Gaussian surface that cuts through slab and is kind of centered up on each side. So it looks a lot like grab one of my sticky notes here, but just to kind of help you visualize, we're making a cylinder, if you will. And that cylinder is going through this slab. If I use maybe my, well, this is not square, but maybe it still looks like a slab. It's actually my coaster here, but I'll use this side so you don't see the pretty logo here. But there is the idea is that this is the slab, and we're going to stick this surface, if you will, right through the center of it. So maybe it looks, I don't know if I should throw it on top or bottom or whatever would be better, but it just kind of sticks to. So that's what I'm trying to draw here. And so when we start this problem and say, all right, let's apply Gauss's law. Gauss's law says if you pick any Gaussian surface and you take the electric field and you dot it into the area, that'll equal the charge that's inside the Gaussian surface divided by the permittivity of free space. So we have to have a closed surface. And so this cylinder shaped thing, if I were to call this the, how about I call it the LS for left side, and this side over here, the RS for right side, and then this surface part, kind of the face of it, we could take this integral and say, okay, so what we're going to do is integrate the left-hand side and add to that an integral of the right-hand side and add to that an integral over its face. And so, again, Gauss's law requires us to do the whole closed surface. So in this case, left and right, and the curved part. All right, now, Gauss's law only works well for things that got a lot of symmetry, or maybe I should also say in here, there's some trickier upper level mathematics we could do, but or could be done. We are not going to do it involving, I guess it would be Math 200 stuff. So I'd like to point that out because you'll come across that later on in your education, but you won't come across it this semester. So for this semester, we're just kind of learning the beginning part and the basic part of Gauss's law. And so we won't do any, fancy, Gauss's law involves Gauss's divergence theorem. And if you do that and then differentiate, there's some neat things you can also do. But for us, we will take the kind of the first level approach and do some symmetry arguments. And so that's where then we come across and say, all right, what do we know here about the electric field? And this is where that concept of lines of symmetry come into place. And so an important part of this discussion or this question was that the y dimension is really far. In fact, they say it's infinite, and the z direction is infinite. And I say that because if I were to just to take a line that parallels the x-axis, so it could be anywhere in the YZ plane, as long as it parallels it, it would be considered a line of symmetry. And what I mean by that is if you took this whole slab and, flipped it around, and so maybe kind of a flip around a z-axis or flip around a y-axis, either way, since it's infinitely long, you get back to the same thing. Maybe this coaster would be a better one because it's kind of a square. But if I were to, flip it so that it goes around a y-axis like this, the same thing. Or if I were to flip it around or maybe I should call that the z-axis because it's towards you, and maybe a y-axis because it goes up, flip it around that one, you get the same thing. And so our lines of symmetry are like this pin here. They're parallel to the x-axis, and they're all over the place. You could have one, since it's infinite, it doesn't matter where you put it. Here, there's just as much charge above it and below it. You can put it here, and there's just as much above and below it. So it was our argument the lines of symmetry will be where the direction of the electric field has to be. So what that tells me, if I drew a bunch of them, is the electric field would have to be along an x-axis or parallel to the x-axis. If I have coming out of the paper z and going up on the paper y, and to the right and left the x, my electric field would have to be along the x-axis. So again, without any more additional mathematics, we're kind of stuck to doing things that have a good deal of symmetry to them. So what we could then argue is that we kind of know what the direction of the electric field is on each phase. So for example, this first integral where the electric field is on the left-hand phase, we'll say it's pointing to the left. Although I guess I got to be careful with that because it depends if the charge is positive or negative. I'll represent it as if the charge is positive, but really I don't know if it is a positive or negative charge. So I really don't know the electric field is to the left over here or not. But keep that in mind because we should also ask ourselves, how would this be different and what would change if it was negative? And the answer, of course, is it's the other direction and we get a minus sign. And if we're just trying to solve for the absolute value of the electric, then we can get the magnitude of the electric field, and then the direction would be either to the left for positive or to the right for negative. This one says an expression for the electric field in the external region. So keep in mind that the question is asking in part the magnitude, but I think also part in the direction. So we'll factor that into consideration at the end here. The right-hand side, again, the electric field would be pointing to the right, at least for positives. Let's talk about positives here first. And so we'll do that one. And then the face one is an important one here because everywhere around the face, it's pointing in the X direction, but the area vector, we bring back my little cylinder loop, the area vector, I guess, kind of maybe right here would be kind of pointing up towards you. So I guess I'll call that the Z direction. And maybe over here at the top, it'd be pointing upward on the screen. And so I guess it would be going in the Y direction. But the point is the area vector here is either pointing in the Z direction or the Y direction or some combination. And it's always perpendicular to the field, which is pointing in the X direction. So knowing that, this right here, when we take the dot product, is going to have cosine of 90 degrees in it. Whereas this right one is going to have cosine of 0 degrees, because again, pointing out of the surface is to the right. And we said at least for positive charges, it's to the right. So there's no angle between the electric field and the area. And this one too. Now this is the left face. The left face is pointing to the left, and the area vector is pointing to the left. So this integral actually becomes EdA, and we'll just put LS because that's the left face. And I took advantage of the dot product where it would be the magnitude. So there it is, magnitude. So I'm going to solve for magnitude times the magnitude of the second one times the cosine of the angle between them. Now, notice that if this was a negative going that way, we would get a minus. So that's kind of the difference here. So we're going to get really the same magnitude, whether these are positive charges or negative charges. So let's just keep moving along like they're positive charges and talk about the magnitude. And see the right-hand side, same thing. It would be the magnitude of the field on the right times the area dA times cosine of 0 degrees, which is 1. And this was an important one here, is that on the face, we would have cosine of 90, which is 0. And so we get a 0 from that integral. And that's really important here because I said something quite interesting here, that I'm going to make sure that I have set my Gaussian surface perfectly symmetric in the slab. So in other words, it's not too far over to the left, but it's also not too far to the right. You see, if I make it evenly distributed, and not really saying how long it is, just evenly distributed, the field over here on the left, I could argue would be the same as the field on the right, because whatever is creating the field on the right is from this slab, and that's the same distance away and the same distribution of charge and the stuff on the left. So these two E's, left and right, are the same as long as I'm thinking in my mind about it being symmetric. So I'll just leave left-hand side and double it for the right-hand side. By the way, that's also extremely useful for the face, because if this had not come out to be a 0, when I go to calculate the electric field, I'm not sure I can argue that the electric field is the same everywhere along the face. In fact, I know I couldn't. I mean, over here, I'm getting further away. And here, in the middle, since the charge distribution is kind of complicated, I would have a hard time arguing that the field is the same value along here. So I'm not going to try to argue that the field is the same everywhere along this face. Fortunately, I don't have to. The angle let it go to 0. So I think it's going to be unlikely. Well, I think we'll find out in the end whether or not the electric field is the same everywhere along the face. And I don't think it will be. I know, well, maybe outside it will. Well, let's see what happens. But inside, I don't think it would be. And so I would have a real hard time solving this if it hadn't been for that cosine of 90 degrees. So fortunately, that one's there. And then also, fortunately, thinking about it symmetric, I couldn't argue, I can't argue that they're the same. Now, if it was shifted more to the left here or more to the right, I couldn't make that argument, and I'd kind of be in trouble here on having two unknowns. So I'd say one is closer and therefore stronger than the other. All right. Now, let me keep working on this, because another crucial step is to argue that the magnitude of the electric field on the left-hand face, so everywhere along this circle, maybe I'll pretend this circle is it, but I kind of tilt it up and look at this circle. The field here and the field here and the field here and the field here would all be the same. And that's our symmetry argument, that, on its side, if I were to draw a line right here, I would have a bunch of charges from the slab, and it would look the same everywhere else on this face. So I can argue that no matter where I am on the face of the left-hand side, it would have the same value. And that's what I'm doing the integral on the face. And so I can factor out the electric field. And now, of course, this, without even doing the integral, is just saying this is the area of the left-hand face. And so it's whatever the area of this little circle is here, which exaggerated out would be this circular end to it. Okay, so that's the left-hand side of this. Now, probably the hardest part of this problem, not to say those were real easy, but those were a lot like the stuff we already did. So hopefully you've seen all those arguments before, you've done all those. This gets pretty hard. What is the charge enclosed? So I better call this page 1, because I think we've got some significant amount of work to do here. Let me just pause on page 1, going on to page 2, and say, all right, how am I going to get the charge inside? And I'm going to do this. I'm going to say, let's add up little chunks of charge. I guess if we made a picture of this, which we kind of did, maybe now that I've drawn so much on it, it would be better to maybe highlight the Gaussian surface here in green, and even highlights maybe in red where the Gaussian surface cuts through where the charges are. Because as we cut through here, the charges would really only be in this little cylinder. If I use my Gaussian here, I guess maybe I would say, well, it cuts through about there and cuts through about there, and it goes all the way around it. And so I need to figure out how much charge is in the whole Gaussian surface. But I do know that the charge is only between the edges of the slab. And so even though the Gaussian surface is, or the Gaussian volume, the volume of the Gaussian surface. So the Gaussian surface containing the charge is really only from the limits of the slab. It's not the limits of the whole Gaussian surface. All right, but still, there's quite a bit of charge in here, and I got to figure out how I'm going to figure out how much charge is within this Gaussian surface. All right, so, but visually it wants to be that. Now, if I go back to my drawing, And I wonder if blue will stand out here. I could imagine then maybe taking a disk of charge and another disk and another disk and another disk and add up a bunch of disks, and I would get the total amount of charge in here. So when I go back here to page 2, I guess I'm really saying here is what would be the charge in a disk? And so maybe drawing a cylinder here and then saying, okay, I'm going to take and figure out how much charge is in one of these disks and then add up another disk and another disk and add up kind of like a stack of a bunch of dimes. If I get a stack of dimes, that'd be a good one right here, and just go, a dime plus a dime plus a dime plus a dime, and say, okay, what is that? What is that total charge? All right, so I'm going to go integral, and I'm just going to put disk under here. So I'm adding up a bunch of disks, but I do have to figure out how much charge is on one disk. So let's call this dq of a disk. Now, keep in mind the concept of charge density. Charge density, rho, is, of course, the amount of charge divided by the amount of volume. So if I'm looking at this little thin slice of a disk, then this dq, for my disk, would be the density of wherever that disk is times the volume of that disk. Now, the volume of a disk, and so imagine this little cut here. I used to have a dime, but I got rid of it here. But, all right, so maybe I'll use this again. This will be equivalent of my disk. Okay, so here's my disk. I got to get the equation for the density, and that's given in the problem. So let's talk about that in a moment. But it's the volume of this disk. And the volume of this disk would be this surface area. So I'll say area A, and then this thickness. And since I'm cutting it along the x-axis, I'm going to make it infinitely thin. Let me call it dx. Now, I might point out the area of this disk is actually the same as, I'll come back to the picture, but it's the area of one of these disks. It's the same as the area, if I make a full cylinder cut all the way out, it's the same as the area of this left-hand side, which, remember, we ended up with in this equation here. And we called it area of left-hand side. And so I don't know if I even should put a symbol here for area, because the area of the disk and the area of the left-hand side, and for that matter, the area of the right-hand side, they're all the same with a right cylinder. And so maybe I should just cross out the fact that it's a disk, and over here on page 1, cross out the fact that it's the left-hand side of the Gaussian surface. They're all the same A. And I'm going to end up getting them on both sides and getting them to cross out. So that's good. It doesn't really matter what the diameter of my Gaussian surface is that I make, which kind of makes sense. I wouldn't expect the electric field to really depend on how big of a diameter of a Gaussian surface I make. This is just a mathematical tool to find the electric field. The electric field has to do with the charging. It has nothing to do with my mathematical Gaussian surface. So I would be surprised if it didn't cancel off. Unfortunately, it's going to. So that's why I'm just not even going to, put the area of the disk or put the area of the left-hand side. They're the same. So I'll just say the area. Okay, so this is the charge on that disk. Now, maybe this is a good place to come to the equation. The equation says, well, it depends which disk we're talking about. Because if you put a grid on here, the center of it is the y-axis, and then the x-axis cuts through the middle. And they say that the equation for the density is some constants times x squared. So that's the density part. So then if I just copy down the area of the disk and the thickness of the disk, dx, all of those multiplied together would give me the charge. In fact, you can kind of see how the charge is going to be then 0 at the center of the disk, where x equals to 0, and then get bigger and bigger and bigger and bigger and bigger until you get to the last bit of charge. Okay. Now, I'm going to use this and put it back into this equation and write it all down here. All right, so the charge inside of my Gaussian surface is an integral of this dq. So it's c x squared a dx. And like I said, that might be the hardest part of this problem. But then, hang on here, why is my dog going crazy? All right, well, probably heard her bark. I don't know why she's barking like crazy, but usually there's a package on the door when I do that, but I didn't find a package, so I don't know. Anyways, maybe I'll find a package later. Hopefully nobody's breaking in somewhere on the side of my house. All right, so that being said, let's factor out things that are a constant. Here's the C and here's the A. And so I have this integral of just x squared dx. And so that is where now we turn into mathematics. Now, we have to set up the limits. Now, the limits, we could go from minus d over 2 to a plus d over 2, since we would want to go and cover the whole thing. Although you probably remember from your calculus class that if you have a symmetric integral, you get the same thing in the negative axis as the positive, and that's what we have. So you could just go from 0 to d over 2 and double it. And so I'm kind of debating which might be better, to go from negative d over 2 to d over 2, or go from 0 to d over 2 and then double. Maybe I'll do the double. All right, so let's call it CA, and I'll put a 2, and then I'll put a limit from 0 to d over 2 of x squared dx. And so usually we write the number first, so I'll put a 2, a C, and an A. And then this would be x cubed over 3, evaluated from 0 to d over 2, to CA again. And then I'll move the 3 over here. Then I will have a d over 2 cubed, so that would be d cubed over 8 minus 0. That's the nice thing about going to 0. I don't really have to mess with that too much. Okay. Although you can see if I did, I would just get the same term. Those would add together and double them. And I wouldn't have that too. So you end up mathematically the same way. All right, so continuing on to page 3, I then would have a 2, a C, an A, and I guess downstairs I would now have a 24. Is that 3 and the 8 make the 24, and D cubed, and a little canceling can occur. And so CAD cubed over 24 would be the total charge. All right. So now let's come back to page 1, where we said it would be 2 times the electric field times the area, and then it would be this charge inside over the permittivity of free space. And the charge inside is what we just did. So that would be a C, an A D cubed over a 12. And this is where I was saying it makes sense that the A shows up on both sides. We would expect or we don't expect the electric field to depend on the diameter of the Gaussian surface we have. Now, what is kind of interesting is you see here then that the electric field does not depend on how long the Gaussian surface is. So we're going to get the same value no matter how long we make it, as long as we're on the outside. So that answers a kind of an earlier question about, well, hey, did I bump something here? Oh no, it's still live on one screen. I lost it on my other screen. I see what I did. Bumped it and it turned off I went to another window. Okay, I thought maybe my camera turned off. Okay, so to finish this finally, I guess I would say that I can bring the 2 over to here and get the magnitude of the electric field is then whatever this constant is, and the width of the slab cubed, and then a 24, and then an epsilon. So that must be the magnitude. Oh, and I guess maybe even to do better is to get the vector form of it. So, all right, let me go one more step further. And we've got the magnitude. So let me put the C and the D cubed and the 24 and the epsilon naught. And let me come back to the picture that I guess I drew here on page 1. We argued that the electric field would point outward if our charges were negative. So that means it would point in the positive direction on the right-hand side, and it would point in the negative direction on the left-hand side. So I don't know if we have an easy way to write that. I guess we could put it, well, I guess we don't really have a way of saying plus or minus in here. So maybe I will put it this way. It is a plus CD3 over 24 epsilon naught in the I hat direction if X is greater than D over 2. So that means it would have to be on the positive side and it would have to be outside the slab. My calculation for the amount of charge would have changed if I was inside the slab. And then write this piecewise, and then it would be a negative C D cubed over 24 epsilon naught I hat. So there'd be a negative direction if X was less than negative D over 2. So that's the 2 regions that the question asked for outside the slab. And I don't think they asked for inside. Derive an expression for the electric field in the exterior regions of the slab. Yeah. So we don't need to do in the slab. Hope that helps. Let's see. Yeah, and it looks like when Don did the solution, yeah, he kind of did the same steps and got the same answer, although he didn't maybe write it kind of piecemeal like this. And that would be fine. I wouldn't deduct any points. That's not the main point of the problem. Cool. Hope that helps.
Yeah, thank you so much. Yeah, that was awesome.
Good.
Well, I guess I will go for now. I might see you later though.
All right. Take care.
Cool. Thank you. You too.